Did you hear that by chance? Okay,
Yeah,
good.
I did.
It's nice to have the announcement so that you know you're being recorded.
Mhm.
Do you have any questions you'd like to ask? That's how I'd like to start. And it's okay if the answer is no.
Not at the time for me.
Okay,
I don't, yeah, no, I don't have any.
I'm going to pause the recording for just a moment because I don't have any paper on my desk. And I'm back. Some of those lecture videos that you watch down the line, you'll see me say things like, okay, so now what I want you to do is work on this problem. And I'm going to pause the video while you do that. And I'll start it again when we start again. And so I pause the video. And when I restart it, I go, and we're back. So it seems like no time has passed if you're watching the video unless you pause it. And you're wondering, what's he doing? Well, you're supposed to have paused. All right. So what we're going to do here is I'm going to move my camera into place here. And we're going to do some problems from the back of chapter 1, probably around the page 24 part, and then we'll go to the page 50 part, which is more interesting. Okay. So let me change my share screen. I wish there was a faster way to do this, but I don't know of it. And you may have seen some of your instructors use a tablet to write on. I've tried that and I can't do it. So that's why I don't do it. Now, here are some problems from the middle of the chapter, around page 20, 22, and so forth. Did we get to this problem here, determine whether kinetic energy is being converted? Does that seem familiar?
It's familiar, but I think it's because I read it myself.
Oh, okay. How about, let's back it up a little more. A solar panel is pictured. When light shines on the panel, it generates an electric current. Have we discussed that one?
Somewhere in your videos, but I've watched a number of them. I don't know if it was in the Zoom sessions. I do know that I've seen that.
How about decide whether the following is a chemical or physical change? Again, if you've seen the videos.
That one I've covered. Yeah.
Okay.
Yeah.
So let's go ahead and let's look at number 18. I think we did number 18 also, where we talked about describe whether this following is a physical or a chemical property. So what I'm going to do is, rather than write the answer, I'm going to point to the things that are chemical properties, okay? Just to kind of do a little refresher. Calcium carbonate is the name of the compound, which is the formula of the compound. That's a chemical property. Reacts with an acid, that's a chemical property. And we could add the to produce, reacts with an acid to produce, chemical property, because the formula of the compound is going to be changing. White is a physical property. Solid is a physical property. The density is a physical property. Gaseous is a physical property. And carbon dioxide, I missed this one. Carbon dioxide is a chemical property. Essentially, a chemical property is one that involves something about the formula or something about it reacting and changing formula. A physical property is something that you could determine without changing the substance into a different substance. So for instance, if you melt ice and turn it into water, it's still H2O. That's a physical property, the melting of it. Here, you can determine whether something's white, whether you're looking at a little bit of it or a lot of it. A nice tiny little gold bracelet is gold colored. Those really big chains that some people wear, they're gold colored. Doesn't matter how much you have, you can determine the property and you're not changing the gold chain into something else. You with me there? So a physical property is something you can determine without changing it into something else or trying to change it into something else. But also sometimes you look at these properties in a different way. And usually a chemical property is one that it's hard to do or hard to undo, one or the other. And a physical property is one that, this is a tricky one because some physical properties are things that are hard to do and or hard to undo. Like if you have powder and you separate it into two piles, is that easy to undo? Absolutely.
Yes.
But if you have a chocolate bar and you cut it in two, is it easy to melt it back together? The answer is no.
Not so
But
easy.
cutting the chocolate bar into two doesn't result in a chemical change because each bar still tastes like chocolate. You haven't changed any of the formulas of the substances. So
Mhm.
There's different ways of trying to figure out what is a chemical and what's a physical, but ultimately, fundamentally, a chemical property is one where you're looking at the formula of the compound or element and seeing if it changes. And sometimes for a chemical property, the answer is no, it doesn't have that chemical property. Like, does a piece of paper burn? Absolutely. And when you're left with the results of that burning, you have ashes, carbon dioxide, and H2O. Those are different substances than they were before. So that's a chemical change. Does a rock burn? No. But that doesn't mean that's not a chemical property. It is one because you've tried to change it. Are you with me there? So chemical property is trying to change it into something else or something about the formula. So down below here, you can see that gray is going to be physical. Powdered is physical. Zinc is a formula, so that's going to be chemical. We could argue both ways on metal, that it's a chemical property and a physical property. We'll learn more about that later. Reacts with chemical. Purple, physical. Iodine, chemical. White, physical.
Physical.
Compound,
Chemical.
chemical. Because we know it's not an element that you get, it's a compound. Okay. So here in the book, there's a solar panel, and you can imagine in your mind what a solar panel looks like. When light shines on the panel, oh, I see what I've done. When light shines on the panel, it generates an electric current that can be used to recharge the batteries in an electric car. What types of energy are involved? And so what I'm going to do here is I'm going to give you the quick spiel on types of energy. You need to know this. And, you know, it's very common for me on an exam to ask questions where your answer is going to be a list or short descriptions. So kinetic energy is the energy of motion. And potential energy is the energy that is stored. Types of kinetic energy are heat, translation, and in my example for translation means moving from one place to another. Okay. Also, there's sound, and there's electric current. Another way to say electric current is electricity. So in translation, we're talking about a rock being thrown, a river flowing, my mouth moving. That's all translation, motion, where you're going from one place to another. Heat ultimately is the vibration of atoms. So even at room temperature, atoms are vibrating and they have energy, kinetic energy. If they vibrate too much, the atoms will move relative to one another and the stuff is melted then. It's a liquid. And when it's melted, if you add even more energy to it, eventually they have enough energy where they will fly apart and it becomes a gas. And when it's a liquid or when it's a gas, when they're moving, there's definitely some translation involved there. But even when the particles are liquid, they're still vibrating when they're moving relative to one another. And when they're gas, they're still vibrating. Okay, sound is also a type of motion, but it's a special type of motion. It's a pulse motion. So I want you to imagine in your mind a jump rope where it's tied to a wall and the other person has the rope other end in their hand, and they whip the rope. So what is going to happen is you're going to get a little hill of movement of the rope along the rope, and it'll hit the wall, right? And when you're done, the rope has not moved. But have you moved energy along the rope? And the answer is, well, put your face there instead of the wall, and you'll find out if there's any energy in that little hump. And there is. So with sound, it's the same way. You're not moving air from one place to another, you're pulsing it. So what's happening here is I'm speaking, you have a little computer or a speaker in your computer, and it's pulsing the air. And so because of my voice, the pulses are something that you can interpret as particular words. But I'm not moving the air away from me, because if I were, I would suffocate if I talk too much. And that never happens, unfortunately, for some of us, right? Maybe for you guys because of me. So sound is a pulse, which is not really translation. Do you understand that?
Mm-hmm.
Electric current is another example where electrons are moving from one spot to another, but it's like a game of musical chairs. Only in this case, there's a chair for every electron. So when the music stops, every electron has a chair. It may not be the chair it was in before, but it has a chair. And every chair that had an electron before has an electron now. So here with electric current, when it's happening, you can't see the electrons moving because they're always moving from one chair to another. And also when you stop it, you can't tell that the electrons have moved. So it's a special type of translation where you can't really tell anything's happening. And it's quite different than sound. Okay, so those are the 4 types of kinetic motion or kinetic energy, which is motion energy. For potential, there is a counter to electric current, and that's called electrostatic. So this would be like static electricity, where you know that there's potential energy there. And if you get too close to something, the electric current can flow and you get shocked. That's an example of a potential energy turning into a kinetic energy. Now, if you're smart and you know that you're going to get shocked when you touch the car, you take your younger sibling and push them against the car, and it's a done deal. You guys know what I'm talking about? I bet you do.
Murder?
No, you have your younger sister touch the car first. You go, hey, can you open that door for me?
Right, right.
Okay, other potential energy. Now, none of these others have a clear difference, except for perhaps translation. Position due to gravity. So this one does not work in outer space where there's no gravity, but it does work here. So here you can see that if I hold up something, so this pen right here, this has potential energy. And if I let go of it, you can see that it drops and it's turned into kinetic energy, translation energy. Now, when I drop it, you can actually hear it hit the table, right? Now, I'm going to move the pen up higher. And because of its position, it now has more potential energy. And when I drop the pen, whoops, it's a little louder. So that means it had more energy at a higher position. So position due to gravity. There's a spring. And I don't mean like a water spring. I'm talking about a spring that you stretch or compress. So a great example of a compressed spring would be your shocks in your car. Now, actually, not your shocks, but the springs that surround the shocks. When your car pushes down on the springs, it wants to push the car back up. Okay. Likewise, if you go over some big bump and your front of your car lifts, the springs pull it back down. Okay. And car rides would be really springy if we didn't have shocks, which mute the bounciness. I don't even know if that's a word, but we're going to pretend it is. All right. And the last type of potential energy is chemical potential. And this is stored in the bonds of compounds. So it turns out that a lot of things have chemical potential. Examples would be TNT, which is a chemical compound that's an explosive. Another example of chemical potential would be ATP, adenosine triphosphate, which people call the energy molecule in biology. And the reason that has energy is because of the chemical bonds. You actually break a bond to help capture the energy from breaking that bond. It's a little more complicated than that, but nonetheless, it's due to chemical bonds. So here's a nice list of kinetic energy, a nice list of potential energy, and nice short definitions of each one of them. You should know this, okay?
Mm-hmm.
We lost Alice. She'll probably be back in just a moment. Okay, so if we go back to this problem here and we say, well, a solar panel is pictured when light shines on the panel. It generates an electric current that can be used to recharge the batteries in an electric car. What types of energy are involved in this? Well, definitely kinetic. And here, when it says electrical current, that's kinetic. We didn't talk about this, but light is also kinetic energy. I went to a website where they actually said that light is not energy because it has no mass. And they're absolutely wrong. And the reason for that is all you need to do is think about this. If you shine light like sunlight on butter, will it melt?
Yeah.
Okay. Does it take energy to melt butter?
Yeah.
Yeah. So light is energy. So saying light is not energy is fairly stupid, in my opinion.
Mm-hmm.
It's kinetic energy because it's moving. Potential energy, the battery. And that's chemical energy. Because when you charge the battery, you're separating chemicals that when they unseparate, they provide energy. So this is what we have in this setup. We have light, which is kinetic, electrical current, which is kinetic, and the battery, which is chemical energy. Any questions on that one?
Nope.
Okay. Then we shall move on. Okay. Now this is a tricky question. Determine whether kinetic energy is being converted to potential or vice versa in the following processes. Water cascades downward in a waterfall. Well, clearly if water is cascading, that's kinetic energy, right?
Mm-hmm.
And when it moves downward in a waterfall, to me, a waterfall is the water falling. So that's kinetic energy. If they had written water cascades downward into a pool of water, I would say that the pool of water is potential energy because it's not really moving.
Yeah.
And the pool has potential because it's going to be at a higher level, and therefore the water will flow out of it if need be.
Mm-hmm.
So this, I think, is worded poorly. It's actually kinetic energy and kinetic energy. Now, another way we could have written this is that water from a dam cascades down in a waterfall. The water in the dam would be potential energy because of position,
Mm-hmm.
and the waterfall would be kinetic energy because of motion. Sound good?
Yeah.
So I don't like the wording of these. A player kicks a football. So here, if we think about the player being in motion, that's kinetic energy. If we think of the football as being stationary, it's got potential.
Uh-huh.
Okay. But if we think about the football being in the air, then it's kinetic energy.
Mm-hmm.
So this, again, is a tricky one. Maybe a little more clear than the one above, but we could say that the player kicking is kinetic and the stationary football is potential. And actually, what you're doing with the football is, although it does have potential, it doesn't have much if it's on the ground.
Mm-hmm.
Because by position, it can't dig itself into the ground. So you're actually increasing the potential energy of the football when you kick it because you're elevating it. And so it will have more potential. But footballs don't get elevated and just stay up in the air.
Yeah.
They immediately change that potential back into kinetic when they drop back down. So again, the nuances here are really tricky. And I don't think that the author who wrote these really thought about that.
Mm-hmm.
Now here, electric current, clearly kinetic, generated by a chemical reaction in a battery. Well, generated, that's going to be kinetic.
Mm-hmm.
When we talk about the chemical reaction, let's say an electrical current can be generated by a battery. The battery would be potential.
Mm-hmm.
The chemical reaction is actually kinetic because things are running into
Moving.
each other. Okay. So again, very tricky. Water boils when heated on a stove. This one's really tricky because if you ever look at water boiling, it's moving. That's kinetic energy. It's hot. That's heat. That's kinetic energy. The flame, the chemical reaction, that's kinetic energy. So where's the potential energy here? And I think what they really wanted you to think about is on a stove, if you're thinking about a gas stove, the gas is potential energy.
Mm-hmm.
If it's an electric stove, the electricity in the wall before it comes out is potential energy. When it's moving and it's current, then it's kinetic energy.
That makes
So
sense.
I would try to write these a little differently if I put them on an exam, so where it's a little more clear about what is what. Like water from a dam flows down in a waterfall. Okay. Next we have number 26. Iron pyrite, fool's gold, has a shiny golden metallic appearance. There's a picture of this in the book. Crystals are often in the form of perfect cubes. A cube of 0.4 centimeters on each side has a mass of 0.064 grams. Which of these observations are qualitative and which are quantitative? So in answering this one, I'm going to move this up just a little bit. So the difference between qualitative and quantitative is easier if you think just about quantitative. So I'm going to abbreviate these words as qualitative and quantitative. Quantitative means there's a number associated with the value or the condition. So here, 0.040 centimeters, that's a quantity. The mass of 0.064 grams, that's a quantity. So every other thing here is a quality, shiny, golden. There is no quantitative measurement of how gold it is. Metallic, crystal, cube. These are all qualitative observations. These are all quantitative. Even the cube, you might say, well, isn't that really a quantity because you have to have an edge? And the answer is, yeah, you do have an edge, but if they say a cube, it could be any size edge. You could have a small cube, or you could have a large cube, like a cube you have in your living room that you're going to use as a coffee table. Or you could have a tiny little cube like, dice. So just saying cube does not make it quantitative because there's no number associated with it, but there is a shape associated with it. Okay. Any questions about A?
Nope.
How about B? Which of the observations are extensive and which are intensive? So I'm going to abbreviate these as extensive and intensive. And the way I remember the difference between these two is extensive depends on to the extent of what amount of material you have. Intensive is an inside quality. So what are the extensive things? 0.040 centimeters and 0.064 grams. Those are extensive because they both depend on how much you have. So what things do not depend on how much you have? And the answer is shiny, golden, metallic, crystals, and cubes. So you can see that when you look at extensive versus intensive, usually the quantitative and the extensive match, and the qualitative and the intensive match. Are you with me?
Yeah.
Okay. So off the top of my head, I can't think of an example where you have an extensive property or observation that is not quantitative. I really can't think of one. Okay, and then C, what is the density of iron pyrite? So what I'm going to do is I'm going to flip this page around here. And to calculate the density, this is the way I always like to see problems like this done. You start off with the formula using variables for the parts of the formula. So D stands for density, M for mass, and V for volume.
Mhm.
And here, I would not expect the person to write down a little legend over here that says D is density, M is mass. So here, sometimes I like to just put in the numbers next to it if it's a very short calculation. But if I'm going to be doing a lot of work, I work vertically. And you've
Okay.
probably seen this in a math class too.
Yeah.
So 0.064 grams is a mass. And to get the volume of a cube, we actually have to take that 0.40 centimeters and multiply it by itself 3 times, because volume is length times width times height.
Mhm.
And in a cube, these are all the same. So this is a perfectly fine way of writing length times width times height.
Okay.
Now, I'm not sure that we have talked about, well, we have talked about in lab, significant figures and scientific notation, not scientific notation, but significant figures. This
Yeah.
has 2 zig figs because leading zeros don't count. This has 2 zig figs because trailing zeros count if you see a decimal. So since this is all multiplication and division, and we have 2 and 2, we're going to be allowed 2 significant figures in our answer. So if we do the work here, 0.064 divided by 0.4, divided by 0.4 again, divided by 0.4 again, my calculator spits out, that can't be right. Let me think about this. 4 times 4 is what, 16?
Yes.
16 times 4 is 64, right?
Mm-hmm.
So the answer is 1. 1.0, so that we get 2 zig figs. Now, this is not the correct answer.
Mm-hmm.
That is the correct answer.
Okay.
And myself, I prefer that fractions be written with the vinculum horizontal, and you avoid doing this. This to me is a no-no.
Okay.
And the reason is because a lot of times if you multiply 1.0 grams per centimeter cubed, you might multiply by 4.2 grams per centimeter cubed and think that things cancel. And in this case, nothing cancels. You get grams squared and centimeters to the 6th power.
Okay.
But it's hard to tell when you write everything like this, whether or not something is in the denominator or in the numerator. You
That
can
makes sense.
tell, but it's easier to make a mistake. So I advise against it. Here, it's clear this is in the denominator. It's clear that's in the numerator. So if you want to cancel centimeters cubed, you better multiply by something that has centimeters cubed in the numerator. And for those words, numerator and denominator, the way I remember them is the numerator is north,
Oh.
and the denominator is down.
Mm-hmm.
This doesn't work in the Southern Hemisphere because the numerator is up, which is south.
Mm-hmm.
I want you to just think about it. I've always wondered this. If you go down to a Southern hemisphere country Do they have globes that are upside down compared to what we're used to seeing? I mean, when I think of South America or even Africa, they're kind of pear-shaped with the fat part of the pear on top, right?
Yeah.
But to people who live in those countries, are they pear-shaped but with the stem down?
I've never thought of that.
Yeah,
That's tricky.
yeah, who knows? I don't. Okay, so this would be the correct answer right here, and this would be the kind of work I would expect to see. Any
So
questions there?
similar to how you do like an algebraic expression, you just keep going until you get the answer at the end.
Yeah, and you can
Okay.
also do it this way.
And then just box your answer at the very end.
And well, actually, I do like the boxed answer. I don't require it. But here
Okay.
you can see that it's a very easy to follow solution. And here you can see it's a very easy to follow solution. So what I'm asking for is that your solution is easy for me to follow.
Okay.
Okay, so that's would be the answer for C. Okay. Which observations below describe chemical properties? And that's as opposed to physical properties. So chemical property means that we're looking for a reaction, something that's changing the formula. And I think it's clear from A that this is a chemical property because of the one keyword reacts. B, water boils at 100 degrees Celsius. We know that when it boils, it turns into steam, but steam has the same formula as water. So this is a physical property, not a chemical. Ultraviolet light converts O2, ozone, to I said that incorrectly, even though it's written right here. Converts O3, ozone, to O2, oxygen. There's a change in formula. This is chemical. Heat is required to melt ice, which we know could be refrozen. This is physical. So if we were to answer this by what they asked, the chemical properties are A and C. Okay, azurite, a blue crystalline mineral, is composed of copper, carbon, and oxygen. What are the symbols of the three elements that combine to make the mineral azurite? Well, clearly copper is Cu, carbon is C, and oxygen is O. Based on the photo, describe some of the physical properties of the elements and the mineral. Are any the same? Are any properties different? So this is on page 24. Let's take a look at the image that we see in our book. Okay, so there's the image. There's the azurite. There's the carbon. Down here is the copper. And they can't really show oxygen because it's a clear and colorless gas. So if we wanted to make a list of the properties, it would probably be something like the following. So the azurite, to me, it looks crystalline. It looks brittle. It looks like it's a solid and not a liquid or a gas. It looks like it's purple with gray. So there are a lot of things that we could write there about the azurite. And there are probably other things that you could write. Now, why do you think I wrote brittle looking at the image?
You could break off sections because it's almost crystal-like.
Yeah, it looks like the shape is not rounded and soft looking, it's jagged. To me, that usually means it's a crystal of some sort. The carbon, it looks like it's black. In this case, it's powdered. And when something is powdered, you don't know whether or not it's a, how do we say it? We don't know whether or not it's brittle or not.
Mhm.
It's hard to tell. You can have powdered metals. Like if you've ever used a hacksaw on a piece of metal, you get these little filings that are almost powder-like. So
Mhm.
I don't think we can make the claim as to whether it's brittle or not, but definitely it's powdered and definitely it's a solid. How do I know that's a solid and not a liquid? And it's really simple. You can make a pile out of solid material. You can't do that with liquids. Liquids make
Mhm.
puddles. So how do you know it's not a liquid and it's not a solid? And the answer is, well, if it's something that you might breathe, then it's a gas. So gases are something you could breathe. You may not want to because there are poisonous gases out there. Solids are something you can make a pile out of. And liquids are things that make a puddle. I call that my second grade definition of the different states because the
Mhm.
second grader would understand all of those. And they'd say, my favorite one is the puddle. Okay, so that's what we have for carbon. And for the copper, it looks copper colored. I mean, that's such a distinct color that we give it a name, copper. It's definitely a solid. Uh, it looks like we have rounded pieces there. So here, this is usually when we see something like that, we call it shot, like something you might
Mhm.
put in a shotgun, actually. Um, can we write anything about at what temperature these things melt based on what we see?
No.
Nope, we can't. There is one more thing we can put about the copper. It's shiny. And the reason that's important is metals are shiny. Non-metals usually are not. And I
Mhm.
think you could look at the carbon and say it's not shiny. The thing about crystals, though, is they invariably, because of their jaggedness, reflect light differently. So they could like kind of shiny, but maybe a better way to put these would be sparkly. Most crystals look sparkly. And I think that's why people are drawn to them. Okay, so we're done with that one. So let's move along. Small chips of iron are mixed with sand. Is this a homogeneous or heterogeneous mixture? So you want to look at that table or that chart where they talk about homogeneous and heterogeneous and compound and pure substance and all of that. And you want to know the difference. Basically, homogeneous means when you look at it, it looks the same everywhere, like a scary store mannequin or homogenized milk or butter. It looks the same everywhere. Homogeneous means it does not look the same everywhere, like people. People don't look the same because we have hair usually on the top of our heads. We've got eyes that are different colors than our skin and so forth and so on. So people are heterogeneous. Um, so what you do when you're looking at things like this is you just look at it. Does it look the same throughout, everywhere? And when you see the mixture of sand and iron, parts of the mixture look dark and parts look light. So
Mhm.
that's a heterogeneous mixture. Okay, so it is totally based on what you see, homogeneous and heterogeneous. Suggest a way to separate the iron from the sand. And tweezers is an appropriate answer, but it is going to take you a long time. A more appropriate answer would be to probably, this is a good way of doing it, is put water in there. So it's kind of slushy and stir it with a magnet. What's going to happen to
Mhm.
the iron?
It's gonna connect to the magnet.
It's going to stick to the magnet. And you pull the magnet out, you take the iron off and you dry it, you got the iron. And for the sand, you pour the water out and you dry it and you got the sand.
Mhm.
So sometimes when you're trying to separate things, you use tricks, if you will, that make your life easier. And water is a great trick because it's easy to evaporate.
Mm.
Okay, identify the following as either physical changes or chemical changes. So again, for chemical changes, we're looking for something where you're changing the identity of the material. There we go. The desalination of seawater, separation of dissolved salts from pure water. So when we do this, are we changing the water in the seawater into something else? No, it's still water. Are we changing the dissolved salts into different dissolved salts? And the answer is no. We're not changing anything into something else. We're just separating them. And in fact, this is how people who live near the ocean used to get salt. They would just take ocean water, put it in a shallow pool, let it evaporate, and scrape the white stuff that remained, salt. And that's how they do it in Salt Lake City. Basically, this has happened over years. A bunch of salt has come out of the water because you have a very salty water there. And what they do is they take salt water, put it into a nice shallow pool, let it evaporate, and then they take a bulldozer out there and scrape it up. It's pretty interesting to see them do that. So when the water evaporates from the salt water, it's still salt. So A is a physical change. B, formation of CO2 when coal-containing sulfur is burned. We know that sulfur is an element on the periodic table, and it's forming SO2. The formula for sulfur is S. For SO2, it's different. This is chemical. Any questions on that one?
Mm-mm.
Silver tarnishes. Now, it's easy to untarnish silverware, but it turns out that what you're really doing is you're scraping the tarnish off. You're not untarnishing it. Turns out that the silver is reacting with sulfur compounds to make the tarnish. So you're getting a silver compound with sulfur compounds in a new compound, and this is a chemical reaction. This is one you probably need to look up. So for the tarnishing there, one of the ways that we might understand that this is a chemical reaction and not just a physical is simply this. The silver is shiny, it's silvery, it's a solid, and then part of it becomes tarnished, which is kind of dull looking, not shiny anymore, not quite as silver, but more gray looking, but it's still a solid. If the silver was still silver, it should look silvery, shiny, and a solid. The fact that it's changed color to gray, the fact that it's dull looking, and of course it's still a solid, two things have changed. When those two things have changed, that's a physical change, but it means that it's probably been a chemical change that has happened. Now, if it's only one physical change, then there's all bets are off because you can have a liquid turn into a gas just by boiling it.
Mm-hmm.
So when you have two different things change, it gives you more oomph behind it. Plus the fact that it's a solid before and a solid after. Tarnish is a solid, silver is a solid. When it's not changing state, you don't expect the color to change or anything like that. So chemical. Iron is heated to red hot. So when you cool the red hot iron, it turns red again, or turns iron colored, whatever you may think that may be. And so this is not a chemical reaction. It's simply a physical change. You're heating it up and then cooling it down. Any questions there?
Nope.
Okay, and that's the end of what I have for that particular part of the chapter. We still have a good 25 minutes left. So what we're going to do here is we're going to go to the second half of the chapter and do some problems from there. Now, remember, it's your responsibility to ask me any questions you may have during my talking. Don't be afraid to interrupt me. Sometimes I get going like a steamroller and it's hard. It feels like I can't get a word in edgewise. That's when you hold up your hands and go, ho, 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 hold on there, Tony. Okay. So,
Okay.
so practice. Blah, 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 blah.
Wait.
Okay, there you go. The temperature of the sun is 5.5 times 10 to the third degrees Celsius. What is this temperature in Kelvin? So you need to memorize this formula. If you want Kelvin, you take the degrees Celsius temperature and you add 273.15. Now the book actually has the following. To get the Kelvin, you take the degrees Celsius temperature and you multiply it by K over degrees Celsius. So I'm going to put X degrees Celsius and you add 273.15 K. So that shows you what happens with the units. Now for this temperature conversion, I'm not interested in this. I'm just interested in you doing this. So if you wrote something like 5.5 times 10 to the 3 degrees Celsius, oh, leave that off, plus 273.15, that would be appropriate. Now,
Okay.
we have to get the right number of significant figures in our answer. And you see how this one is in exponential form and this one is not? Or we could call this scientific notation. I'm going to write this out. This is 1,000 times 5.5, which is 5,500. Now this has 2 zig figs. So when we write it out this way, we'd like to show 2 zig figs. This has 2 zig figs because trailing zeros do not count. So when we add these together, we can see that this is going to become 5, and this 5 and this 2 are in the same place. So that's 773.15. So that would be the Kelvin temp, but now we have to round appropriately. And when we're adding two numbers together, the way to round is to round to whichever number is least precise. This is precise to the hundreds place. This is precise to the hundredths place. Since this is less precise, we need to round to right there. So this becomes 5,800 Kelvin. Any questions there?
No.
Okay. So make the following temperature conversions. Why don't you go ahead and see if you can make these temperature conversions? And when you're ready, give me a little nod and we'll look at what I get compared to what you get. Or have you already done this?
I have not done this one.
Okay, so you know the formula, but you'll notice that sometimes you have to do the opposite. You have to not get the Kelvin temp, but you have to get the degrees Celsius. Now, let me show you just quickly my take on this. So if you want to get Kelvin, use this formula. If you want degrees Celsius, you want to write this. Notice I've rearranged the equation so I have degrees Celsius on the left and everything else on the right. And how did I do this? Well, let me show you. Now, this is something I expect you to be able to do and not be able to, and not have to show all the work, but I'm going to show you the work, okay? So I'm going to add a negative 273.15 to this side, and I'm going to add 273.15 to this side. So I get K minus 273.15 is equal to degrees Celsius. I don't expect you to show me that work. Here, the laws of algebra say that if A is equal to B, then B is equal to A. So that's how I got that equation. Again, I don't expect you to show me all that work to get here. I expect you to get this correctly. Now, when you have equations like this, it makes a problem like this so easy, because if we want degrees Celsius, we're going to use this form. And if we're going to get Kelvin, we're going to use the one above right here. And part of the challenge in chemistry is to make it so that it's hard for you to make a mistake. The setup is important. So when you're ready, give me a shout. Remember to round correctly. And I'm actually doing this as we speak. Okay, are you ready?
Just 1 second. All right, I'm ready.
All right, for A, degrees Celsius is going to be Kelvin minus 273.15. So we have 77 minus 273.15. So I got minus 196, I think. And actually I got minus 196 point something, but this is good to the ones. This is good to the hundreds. So this answer is going to be good to the ones. So that's why I rounded to the 6, which is in the ones place. Okay, that's A. For B, we have 63. So Kelvin is going to be 63. And here, let me write out what I would want to see. Kelvin is degrees Celsius plus 273.15, which is 63 plus 273.15, which is 336. And it's actually 336.15, but we would round to the ones because this is good to the ones, this is good to the hundredths, and the ones is less precise, so this would be 336, and that's the Kelvin. Any questions on B?
Nope.
C would be degrees Celsius is equal to Kelvin minus 273.15, which is 1450 minus 273.15, which according to my notes is 1176.85. This is good to the tens. This is good to the hundredths. So we want to round to the tens. And if you wanted to, you see how I put an arrow pointing to where the last significant digit is when we're look farthest to the right? I could put this arrow here and I could put this arrow here. And where do we round to? Well, going from the left, you round to the first arrow you see.
Okay.
So 1, 1, the 7 becomes an 8 because of the 6, and you put a 0 there.
Okay.
And this is 3 significant figures.
Okay.
Okay.
Yeah.
The average lead pencil, new and unused, is 19 centimeters long. What is its length in millimeters and in meters? So let me show you how to do this. I'm going to show you how to convert a couple of ways. So we want to take our 19 centimeters and turn it into millimeters. This is my roadmap, if you will. I don't expect to see this on a test, but this is for you to understand how I'm going to come up with a solution. So I want to be able to convert between centimeters and meters. And I happen to know that 10 millimeters is equal to 1 centimeter. I happen to know that, okay? So I can take my 19 centimeters and I can multiply by this. Now, when I say multiply by this, what I'm going to do is I'm going to change this so that one part is on top and the other part's on the bottom. So that means I could change it to this, or I could change it to this. And I know you can't see what I'm writing, so I'm going to give you a moment to see.
Mm-hmm.
I can change it to the first one where I put 10 millimeters on top, 1 centimeter on the bottom, or I can change it to 1 centimeter on top and 10 millimeters on the bottom. This is equal to 1 and this is equal to 1.
Mm-hmm.
So you can mathematically change this into this and get that or that. Now, which of these two am I going to use over here? Well, if I want to get rid of centimeters, I'm going to use 10 millimeters over 1 centimeter because this is in the numerator. Sometimes it's hard to tell. So what people do is they do this. They use the identity law, which says if you divide anything by 1, it's still the same number.
Mm-hmm.
So here it's really easy to see that's in the numerator. I don't normally do this. But this centimeter cancels that centimeter. And that millimeter does not cancel, so we're left with that. Now, when we multiply these, we get 190 millimeters. And this is one way to do it. Now, how many significant figures are in the 19? 2.
2.
How many significant figures are there in the 10 and the 1? These types of metric conversions are defined, which means the 10 has an infinite number of significant figures. The 1 has an infinite number of significant figures. So if we've got 2 infinity, infinity, we get 2 zig figs. And by our definitions, this 0 doesn't count because you don't see the decimal.
Mm-hmm.
Now, let's say you did not know this. How would you do this conversion? So I'm going to call this A. What you would do is you would take your 19 centimeters, convert that into meters, and then convert the meters into millimeters. And so here's the deal. For this very first conversion, we know that 1 centimeter is equal to 1 centimeter. That's a fact.
Mm-hmm.
But we also know that centimeter really means 10 to the minus 2. That's a fact. Now,
Mm-hmm.
I'm not going to change both of the C's. I'm only going to change one. This is my conversion from centimeter to meter. So I can write 19 centimeters times. Now, one of these goes on the bottom and the other on top. Which one am I going to put on the bottom?
Centimeter.
And which one goes on top?
The 1 times 10 to the negative second.
Okay. So now I have meters. So for number 2, I want to go from meters to millimeters. And notice I do the same thing. 1 millimeter is 1 millimeter. So what is a milli equal to?
100?
No, milli means
Or
a
1,000.
thousandth. Thousandth. So 10 to the
Mhm.
minus 3. So here I'm going to put 1 millimeter on top and 1 times 10 to the minus 3 on the bottom. Now, a lot of people do not like working with numbers like this.
Mm-hmm.
So what happens if I divide this side by 10 to the minus 2 and divide this side by 10 to the minus 2? This cancels, right?
Uh-huh.
But I'm going to show you something that's a little more clever. What happens when I multiply this by 10 squared and I multiply this by 10 squared? 10 to the minus 2 times 10 to the plus 2 is 10 to the 0, which is 1.
Mm-hmm.
So here, and if I want to write this out, I get 100 centimeters is 1 meter. So this is the same thing as saying 1 centimeter is 1/100th of a meter. I want you to visually think about that. Here's a meter. Here's a meter.
Mhm.
How much of this is 1 centimeter?
100th of it.
1/100th of it. 1/100th of it. This is a centimeter. How many of these do I need for 1 meter?
100.
100. So do you see how this that I have my fingers underneath says you need 100 centimeters for 1 meter? And people are usually more comfortable with that rather than this, which says you need 1/100th of a meter to be 1 centimeter.
Mhm.
Humans are more comfortable not working with negative exponents. So
Mhm.
what would this one become? This one would become 1,000 millimeters is 1 meter. And so we could have written this, and this would also be appropriate. Both of these are absolutely fine. Okay.
Okay.
And both of them provide the same answer, 190 millimeters. So of these 3 solutions that I've shown you, which one is the best? And the answer is half a dozen of one, 6 of another, meaning they're all the same.
Mhm.
They're all the same. It's just what you're more comfortable with. As long as you are showing what you're beginning with, how you're converting, you have the units, you report the answer with the correct number of significant figures, that's what's important. So if you want to do it this way, fine. If you want to do it this way, fine. Or this way, they're all fine. But I will say that this is kind of easy when we say 100 centimeters is 1 meter. 1,000 millimeters is 1 meter. But what if I asked you about micrometers and meters? What would you write?
Micro's 10,000, right?
Micro is 10 to the minus 6. So if we did it the way I've been talking about, it would look like this. Micro is the Greek letter mu, which looks to me like a cursive U with a long tail at the end.
Uh-huh.
So then I would write this, because mu means 10 to the minus 6, or I should say micro means 10 to the minus 6. And then if I take this to the other side, see, that's kind of a neat trick. If you have 10 to the negative exponent, when you move it to the other side, it becomes positive.
Uh-huh.
So what is 10 to the 6? It's 1,000,000. So that would be correct, 1,000,000 micrometers. What would be the case for a nanometer? A nanometer is 10 to the minus 9. So it would be 1,000,000,000 nanometers is 1 meter.
Mhm.
Okay. Now, what if I asked you about centigrams? What's the relationship between centigrams and grams?
100 centigrams is 1 gram.
That's correct. It's the same as this, only instead of M, we use G.
Because you just need to know the quantities that goes with the
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 letter.
preface, right? Pretty
Yeah.
much.
Exactly. So I usually work in exponents, so I don't have to work with such long numbers like this.
Mm-hmm.
So just a quick review of exponents. 10 to the A times 10 to the B is equal to 10 to the quantity A plus B. So an example is 10 to the 5 times 10 to the negative 6 is equal to 10 to the negative 1. 10 to the A over 10 to the B is equal to 10 to the A minus B.
Okay.
And ultimately, the way this works is if you have 1 over 10 to the B, that's equal to 10 to the minus B. So what I say here is, you see this 10 to the B, and this is a line.
Mm-hmm.
Cross the line, change the sign.
Gotcha. Okay.
So if you had 10 to the A, you could write that's equal to 1 over 10 to the minus A.
Okay.
Cross the line,
ma-
change the sign.
Okay, that makes sense.
And let me show you why that works. So mathematically, we know that if we multiply by 1, we're not changing the value, correct?
Mm-hmm.
So I'm going to multiply this by 10 to the minus B over 10 to the minus B. And I would argue that that's 1 because the number up top is the same as the number at the bottom.
Mm-hmm.
The top becomes 10 to the minus B. The bottom becomes 10 to the, based on our rules above, B plus minus B is 0. And any number raised to the 0 power is 1.
1.
So if I clean it up, you can see that essentially what was on the bottom, I switched sides and changed the sign.
Okay.
So cross the line, change the sign. Do you know what this line is called? I ask
do.
math teachers this all the time, and they don't know the answer.
I used to know. At some point I did.
It's called the vinculum. Now, that probably doesn't sound familiar to you because no one knows that. You know how
Yeah.
I know it?
Hmm.
I know it because it was on a Snapple cat.
Huh.
But
Interesting.
I always wondered, what do you call the dividing line? And they go, the dividing line? I'm like, but no, there's got to be a name for it. Like there's a name for everything.
Mm-hmm.
I don't know. Vinculum.
Interesting.
Okay. So going back to this problem here. What is its length in meters? Now, this one is even cooler because I can show you 2 ways to do it. So we know that we want the relationship between centimeters and meters. So I start off with the prefix. 1 centimeter is equal to 1 centimeter. So 1 centimeter is 1 times 10 to the minus 2 meters. Then I can move this to the other side. 10 squared centimeters is 1 meter. And if I don't like the square, I can write 100 centimeters is 1 meter. After you do this a few times, it ends up taking you 15 seconds, which is 15 seconds well spent.
Mm-hmm.
So we write 19 centimeters times 1 meter over 100 centimeters, and we get 0.019 meters. This has 2 zig figs because leading zeros do not count.
Mm-hmm.
Now I'm going to show you an even cooler way to do this. C means 10 to the minus 2.
Mm-hmm.
So I don't have to write C, I can write 10 to the minus 2. This is called substitution. And in fact, it's what I'm doing right here. I'm doing substitution.
Mm-hmm.
So C is not real. It's a placeholder for what's real.
Mm-hmm.
So I'm just putting what's real there. So for something that's like this, where you're going from a prefix to no prefix, substitute the correct amount. But you have to memorize the amounts. So
Mm-hmm.
mega is 10 to the 6. Kilo is 10 to the 3. Deci is 10 to the minus 1. Centi is 10 to the minus 2. Milli is 10 to the minus 3. Micro is 10 to the minus 6. Nano is 10 to the minus 9. And pico is 10 to the minus 12. Those are the ones that you should memorize. And then there are more than that. Like beyond mega, there's giga, which is 10 to the 9. And beyond giga, there's tera. And you've probably heard of those when you talk about computers. Oh, that's got a gigabyte of memory.
Mm-hmm.
What's a gigabyte? Oh, a billion pieces of information. Gosh, that's a lot. Okay. Any questions about this one?
No.
Okay, so we'll put that one to the side. Oh, and it's 11:16. So what I want you to do is if you appear Monday, I want you to remind me that we're starting on number 8.
Okay.
Okay. Unless you appear in the afternoon, in which case it may be a different number that we start with on for the afternoon section. Fair enough?
Okay. Fair enough.
Okay. Toodles, turn your mics on and say goodbye to everybody.
Thank you for your help.
You bet. Bye-bye.